So in this chapter, we're going to look at positive operators and square roots. So we say that a self-adjoint operator is positive if and only if the inner product between T of V and V is non-negative. So it might be better to call it a non-negative operator, but the standard terminology is to call this positive. And so when you see this, you should think of this as we're comparing the input of an operator to the output of an operator, and what we find is that they're in the same general direction. So by general, I mean that one is not necessarily a scalar multiple of the other, but they're kind of generally pointing the same way within an angle of pi over 2. So for instance, if I take my vector v to be looking like this one right here, then I consider the orthogonal space. Don't know if I do that perfectly right, but so here's everything orthogonal to that particular vector. Then when I look at the output TV, it's going to be somewhere on the same side. It might be shorter or longer. It might be one direction or another direction, but it's going to be on the same in the same half space as the original vector v. Okay, so that's the idea of a positive operator, and this defines actually an order relation. And so this is sometimes called the standard order relation on the self-adjoint operators. And so we say that t is greater than or equal to s if and only if t minus s is a positive operator. So then you can ask yourself questions like, what about a sum of positive operators? Is it going to be positive? What about the product of positive operators? Is it going to be positive? And I claim that with looking at this picture will give you intuition, and then from that you should be able to prove your hypotheses using the algebraic formulation of positivity. Okay, so some examples. The projection is positive, and that's orthogonal projection to any subspace U. We also saw back in the proof of 726, 726, that t squared plus bt plus ci is positive whenever x squared plus bx plus c is irreducible over r. Okay, so there's a couple examples of positive operators. So a rotation about a small angle, like small meaning less than pi over 2, is going to be positive, but a rotation over a bigger angle might not be. A reflection, not going to be positive probably, right? Scaling is going to be positive as long as you're scaling by positive numbers, otherwise you've got a reflection. So there's some examples. Okay, so that is a positive operator, and now for the idea of square root. So we say an operator, and we'll use R, is a square root of t if and only if when you square it you get t. And so squaring here is of course composition, so it means applying it twice. And so there's lots of analogies with the idea of square root of number, but then there's also other things that maybe you might not expect. For instance, some operators have a whole lot of square roots as opposed to numbers, which always just only have 2, right? So if R is a reflection. Then R squared is equal to the identity. So R is a square root of the identity. So right off the bat, the identity has a whole ton, as long as you have at least a dimension 2, the identity has a whole ton of square roots. And there's more. So if R and is rotation by pi about some axis, and so here we're assuming that the vector space is some Rn or Cn. Then R is a square root of the identity again. Because if you rotate by pi and then you rotate by pi again, you've rotated by 2 pi, which is the identity. If we take, let's look at it in terms of matrices. So if we have that the matrix of T is A, B, C, so diagonalized, then the matrix with entries root A, root B, root C defines an operator, which is a square root of T. And then note here that you can pick either value of the square root. And so the standard terminology is that whenever you see this symbol, unless somebody deliberately puts a minus sign in front of it, you always assume that this is the positive square root, right? But we could choose like a negative square root here or there if we wanted to, and it would still define a square root of T. And so how many possible square roots does a diagonal operator have? Well, if the diagonal operator has n entries coming down the diagonal, then it's going to have 2 to the n square roots like this, because you've got 2 choices for each of those n signs.